In the name of God, the compassionate, the merciful, engineering plasticity, chapter 5, plastic analysis of bending, part 2. This is a continuation of the previous part, and we are showing here the cross section of the rectangular beam. This cross section has a width of equal to b and depth equal to h, and that's the neutral axis NN. Now we obtained previously that elastic strain is equal to y divided by r, and we have this general relationship between stress and strain, sigma equal to EA, a constant times the elastic strain, and a constant times elastic strain to the power of n. That is the elastic plastic behavior of a material in general. Now we are going to use these equations in here. First of all, the loading on the beam is m. Now we consider a section of the beam like that in the cross section, distance y and thickness dy. So for this section, the bending moment delta m for this element, delta m is equal to sigma times b times dy times y. Now b is the width here, and dy is the thickness. Therefore b times dy is that area of the element, and times sigma, that area times sigma gives us the force, and force times this distance gives us the bending moment, which is delta m for the element that we are considering. So we get that. And if we substitute for sigma here, we substitute for sigma like that. Okay, so we have dy in here, b in here, and instead of e in this relationship, we have substituted y over r. So we have, if we put for sigma equal to that, and for e equal to y over r, then these multiplied, we get this. Okay, and we have this element here. Now the section changes between plus h over 2 and minus h over 2. So that's the limits of our integration, and we can obtain the bending moment. That is the bending moment. E is constant, r is the radius of curvature of the neutral surface. So E over r and f over r are constants, and therefore we can write E over I times I1, which is this integration, and f over Rn times In, which is this integration. Okay, so that's the short way of writing this, and therefore I1 is the integration by squared dy, and In is by to the power of n plus 1 times dy integration. Now for the elastic case, which you had in the strength of material, we simply put E equal to 0, okay, E equal to 0, and we get m over In, f over Rn, and sigma over Yn. And also, if we put n equal to 1 for elastic case, we get m over I, f over r, sigma over y, which is the usual equation for the elastic case in the strength of material. Now, let's go further and discuss the elastic plastic behavior of the bending moment and see how it evolves. Okay, so if we take an ideal materials in bending like that, ideal material is like this. We have elastic loading, and then when we reach the plastic part, it's rigid plastic. Okay, so that's elastic, rigid plastic. We could write this behavior like this: sigma equal to E times E for the elastic part, and sigma equal to Y for the plastic part. And for the perfectly elastic case, obviously, as I mentioned before, sigma is equal to E times E, and E is equal to Y over R. Therefore, for the elastic case, supposing all the section is elastic, we haven't reached Y yet. We are somewhere in here. Okay? So, let me just, supposing we are in the elastic part, somewhere in here. Okay? That point is represented by that, and ME is M elastic. We just integrate the previous equation for the elastic part. Okay, so we neglect the plastic part and only the elastic part as shown in here. You see, here we have this elastic and that's plastic. So I just integrate the elastic bit, and I get BE over 3R times Y squared between these limits, and if I put the limits, I get ME equal to BE HQ over 12R. That is the elastic bending moment. Okay, we had this in the strengths of material for the rectangular section. Now we move to incipient yielding. Okay, for incipient yielding, ME, that's the elastic, is equal to that, and we have this relationship. So instead of E over R, I put sigma over Y. This Y is just this distance. Okay, so that's the elastic bending moment. Now if I put sigma equal to Y, okay, because we are considering this element here, so I put sigma equal to Y and Y equal to H over 2, because we know that the maximum stress happens here or there. So I'm talking about the tensile loading now. So I just put Y equal to H over 2, and I get ME at sigma equal to Y is equal to MY, and I just put Y in here, and instead of Y, small y, I put H over 2, and therefore I get My equal to BH squared Y over 6 at this place. It means that incipient yielding, the first yield or incipient yielding happens at the top or bottom of the beam, and the magnitude is equal to BH squared Y over 6. Okay, so that is the load needed for the top fiber to yield. We have obtained it here. So we started from the elastic, now we have reached the incipient yielding, and now go to the elastic plastic solution. Okay, elastic plastic solution. Now, as you can see here, we have shown these two figures. What are these two figures? In here you can see that the top part, this colored one, has become plastic. Okay, in the previous slide this fiber was plastic. Then if we increase the bending moment, this plastic region progresses inwards like this, and this one also like that. Now in these two figures we have taken this element again to obtain the elastic plastic solution, but here, because we have this area is elastic and this area is plastic, we have a boundary between them. So I marked the boundary in here as y prime, and I have taken one element in the plastic region and another element in the elastic region, because we can't solve it with one equation. We have to have two equations, one for the elastic, one for the plastic. So we go ahead like this. Now the bending moment is the integration of the elemental moment on this element. Okay, so y prime to h over 2, that means from this to there. And here we have the plastic part. Okay, and we have assumed that in the plastic region we have a rigid plastic material. So if it is rigid plastic material, the stress in here is equal to y, because it's constant, and that's the yield point. That's the stress. Now that is the element, so the area of the element is dy times b, dy times b times y gives us the force, and force times distance y gives us m. Okay, so that is the bending moment for the plastic part, and the bending moment for the elastic part also is like before, Ey over r times y b dy. In fact, Ey over r is equal to sigma. Sigma times b times dy gives the force, and times y, distance, gives us the moment. So that's for the elastic part, and that's for the plastic part. So that's our equation. Okay. Now, therefore, if we integrate and substitute, we get this. Okay, this relationship, and everything here is known except this y prime. We don't know where the boundary is. Okay, boundary could be anywhere depending on what, but how much is m. As we increase the m, this boundary moves towards a neutral axis. We can write a general equation like this. If we put y equal to y prime, okay, the interface, that's the interface, because y prime is the interface. Okay, so if I put y equal to y prime in here, why did I put y equal to y prime in here? Because this is the equation for the elastic material. Now the elastic material finishes here. So if for that y, the end of it is here. So I put this y equal y prime, like that. And therefore I get E equal to sigma times r over y prime. And because at the interface, sigma is equal to y, therefore I could write E equal to y r over y prime. And if I substitute here, for E, I get y r over y prime, and I get this equation. And if I simplify this equation, therefore the bending moment for the elastic plastic case is yb h squared over 4 minus y squared over 3. You can see that if I put y prime equal to 0, all the material in the cross section becomes plastic, and I get yb h squared over 4. And if I put y squared, y prime, equal to h over 2, okay, I will get the all incipient yield. Now for perfectly plastic, I use the same equation as I mentioned in the previous slide. So this is the elastic plastic part. So I move, if I want to get totally plastic, perfectly plastic, I get this coming to here. So y prime is equal to 0, all the cross section becomes plastic. So I put y prime 0, MEP y prime equal to 0 equal to that. Therefore MP. MP means that plastic bending moment, the value of the bending moment required to make the whole cross section plastic. So that becomes EH square y over 4. Okay, so in this way all the cross section from here to there and from there to there becomes plastic. Now we have something called shape factor. Okay, shape factor in fact is defined as S equal to MP over ME. MP is the plastic bending moment and ME is the elastic. In fact, we want to know how much is the capacity of this beam with this cross section to carry load, bending load. We define it like this. We say that the maximum load that it can take until it becomes completely plastic is MP, and completely elastic is this. Therefore, the ratio of these show how much this section has a capacity for taking loads after the elastic load is finished. Okay, so we could say that the capacity to take more load after the elastic point. And for the this cross section, which is a rectangular cross section, we get MP equal to 1.5 ME. In other words, S is 1.5. Okay? The more is S, the more capacity the section has for taking load.